Today we're going to talk a little bit about some of the special topics that relate to kinematic work and kinetic work, but mostly kinetic, and that's where you get it from with the force application. We're going to talk about power, work, and energy, and then we're going to talk a little bit at the end about a braking impulse and a propulsive impulse. So that's where we're going to start a little bit, and we're going to start with the concept of impulse. And what impulse is simply quantifying how much force is applied to a product or an object over a period of time. It's represented by the area on the curve of that force time curve, and then we're going to take it as Newton seconds. Okay, so if we have a jump here, so on the y-axis you see we have force. This is not normalized force, so this is actually just newtons. Sometimes you'll see this as 1, 2, 3, 4, and those are body weights, not newtons. And then we have seconds. What you'll notice is right here, this is at 0 newtons. You should be able, at this point, be able to tell me what that means, and that is when the person is in the air. And then you'll see this portion at the beginning here where the person is, where the value is not really changing. It's fluctuating a little bit, but it's not really changing. And this would be that body weight of the individual. This phase here, we would call that the counter movement. So the downward motion, and then we have the upward motion leading to jump. And so what we would do typically from this is we would have a jump impulse. And so the jump impulse only looks at this first portion of it that we just talked about in this graph. It doesn't look at this because this is the landing portion of it. So the jump impulse is going to be this area leading up to it. Now, if I look at this graph on the right-hand side, what you'll see that they've drawn a line all the way across. What we call that is that's the body weight impulse. This is the impulse or the force over time that is related to the body weight. And you notice it dips a little bit here, and you can subtract that if you wanted to take that area, but we don't worry about that. The jump impulse that we talk about is this area above the body weight. So again, body weight is just keeping the person on the ground in contact with the ground. But in order for the person to leave, they have to produce a greater force than their body weight to jump. So if we take a little area into the curve here, we could calculate that. So every time segment on the process, we calculate what the area is in the curve. Typically we use rectangles, trapezoids to do this calculation, but you're basically just calculating the area in the curve, change in time under the change in force on top. And we talked about the impulse part of it, so that is the force over a period of time. Now what is the effect of that force over a period of time? And that's this other portion of what you see on top here, and that's momentum, or the rho. And that is simply the movement of the mass, describing the movement of the mass from or object as the mass times what happens with their velocity in response to that impulse. It is expressed in kilograms per meters per second. How are these related? Well, they're related by this impulse momentum relationship. Okay, and what it is if we start with force equals ma, or Newton's second law, we break it down into its components, right? So here we have velocity. The acceleration becomes the two components, velocity over time. Then if we divide both sides by time, we get on the left-hand side force applied over a period of time equals the change in that mass's movement. And that is essentially your impulse momentum relationship. So the impulse is the measure that is needed to change the momentum of an object. So if we know the applied force over a period of time, we can calculate how that is going to have an effect on the movement of that particular object. Or if we see the change in the object movement over a period of time, we can calculate how much force was applied to that. Now keep in mind that this is just F. If it was at an angle, we would have to compose that into its X and Y components, or vertical and anterior posterior components, to calculate this movement. Taking this further, we want to talk about what is the effect of applying a force over a distance, and that's where we have the mechanical work concept that comes into play. And this is the effect of force application over a distance. So here, like I said in the previous, I've actually taken in here and kept the cosine in here because I want to make sure that we know that, and very rarely does force get applied in the direction of movement. So if the force is being applied at an angle to the movement, then we need to keep the cosine in there. But here we have work on the left-hand side equals the force applied times the distance at which it moved. Work equals force times distance. Taking it further, so we'll talk about joules, and joules or Newton meters is what the units of measurement are. But we'll take two instances here for you. Pushing force is the force on this equation, and this is where it happens. And pardon me for the use of block, but it's the easiest way to represent this. We could have a person pushing something, but here you have the theta, and at this one, right, it's at 90 degrees, so we know that the cosine of that is 1. Here there's some angle at which it is pushing. So this angle here is the cosine of how much of the force is being applied into pushing the block in the imposed direction. Now we'll know that if the block starts to be from here and it ends here, that's the distance at which it works. So the mechanical work is how much force times the distance at which there's a change in position of whatever the force is applied in that direction. Taking this further, we'll look at mechanical power and what power is. We talked a lot about power in class, and people throw it around a lot. But it's a measure of how much work is done over a period of time. So this is going to be work over time. That's what you have here, work over time. And we're going to take this a little further, as you can see down below, and what the common way we measure this is. But now we have watts, which are joules per second, because there's your unit of time. And then if we look at how we break this down, work over time, we break down what work is. You have force times distance. But if we look at this here, we break that down to velocity. So what you guys will be looking at in the lab this week is how to calculate force and velocity and make that power. So if somebody is more powerful, they're applying a force quicker than somebody else is, or they're applying the same force quicker, or they're applying a greater force over a slower velocity. So there's many ways to increase your power by identifying either the velocity component or the force component. So one of the final concepts, we'll talk a little bit about energy, and specifically mechanical energy. Kinetic energy is the result of motion. You have 1/2 mv squared. Potential energy is the capacity at which something has to do work. And it's a function of your mass, typically gravity in the airborne, and how high you are during the process. And the final one is strain energy, and this is one comes into play a lot when we're talking about this mass spring model in different springs, but it's how much is stored, what the potential energy is stored within a compression or a tension. And so here you have it 1/2 K delta XT, and here is your spring constant right here. So going back a lot to what we talked about with mass spring model, here you have it represented. And what does this look like? Well, it's really effective of the law of conservation of energy, and that states that you cannot create or destroy energy, so there has to go someplace. Total energy within the system is comprised of the potential and the kinetic energy at any given time. Live in this model during an upward flight, and you can follow this. The potential is 0 because they're at the ground, and that's where the kinetic energy moves during takeoff. Its greatest vertical velocity is just right at takeoff. As something goes up, its potential energy increases and its kinetic energy decreases until it reaches the max height, where, if we look at this mv squared, the v is 0, therefore the kinetic energy is 0. Potential energy is mgh, the greatest height, same mass, so at maximum for the potential energy. If we do the reverse, it's going to do the same thing here. When we start at the top, potential energy is the greatest, potential energy is the least at the bottom, when it just before it hits the ground. Okay, so follow this around, and this is, keep in mind this has a lot to do with your projectile motion concept, and how you can dictate what you can calculate the kinetic energy of something just before it hits the ground by knowing its potential energy, because it should be equal. Now, I wanted to take a second and talk a little bit about running because, you know, me and I'm an endurance runner and we talk a lot about it in the class. But I want to bring it from an impulse perspective and how we calculate this as two components. In running, it's braking impulse versus propulsion impulse. And what I have here is on top, you have a traditional ground reaction force component that actually has the three components, and you'll see the vertical, anterior, posterior, medial, lateral. What we're interested in is this anterior, posterior component, and that's the braking. So if I'm traveling this way, anything that is opposing me is a braking, and it's helped me go this way is a propulsion. Now, if you look at this one on top, and the 3-0, you'll see the black one starts off positive and goes negative. Well, that's because of the reference system of the force plate. And it's a little misleading because this first half should be the braking and the second half should be the propulsive. So I kind of wish that the people who illustrated this in their graph that I took it from off the internet had it flipped the other way because it would make more sense. So we look at this graph down here, and I'll call that B graph because this is from some data that I have in my in my stuff. Now this is raw data, so you see it very jaggedy at the bottom here. I haven't filtered this data at all. But if I talk about this and we'll say from here to here is one stand space, okay? Taking that into anything below 0, so this right here, if I take this area in the region of the curve, that gives me my impulse that is working in the negative or working against me. We call that the braking impulse. Anything up here is going to be the propulsive or positive impulse. That is using to increase it. So remember, if we had the momentum, we talked about delta V, okay? And so the braking impulse causes this value to go down because it's reducing the velocity. The propulsive impulse causes it to go up. Therefore, it's an increasing or propulsive impulse. So this is how you use impulses to identify braking and propulsive nature. And you can talk about this from, a lot of people use it from a stride frequency perspective or stride length and see the effects on the amount of energy needed to slow down and speed up. And there's a ratio you can produce here to talk about the need for that. So I just wanted to take this a little further for you and look at this. And so this is a VA force component profile of the PVA relationship. And so if you look at here, we have heel contact at this point. Let's look at the AA graph and toe off here. So this is the period of time that the foot is interacting with the ground. And you can see the horizontals when they're in the air are constant. But if we look at this now during the support phase, during the mid stance, and again, this is going down, the velocity is decreasing. Remember, so if that's M delta V, we know that this is a braking impulse because the MV is decreasing. On the second half of it, it's increasing, so we see that it's the opposite component. So we have the braking and propulsive impulses. Now, if we continue this down, we have this, here is the acceleration profile. And again, negative and positive. So the way that they're changing it, greater, slower, and then the force profile. And this is, if you look at this force profile, that goes back with what we talked about and what you saw just a few moments ago. And if we highlight here, that's our braking in the purple. And then if we highlight in the orange, and we take these impulses, or the areas under the curve, we integrate those, then we can find out what the braking and what the positive impulses are. So here we have it, braking, slowing down, propelling, speeding up.